Yeah, that's good.
Fantastic. Thanks for the introduction. Thanks a lot for the organizers for inviting me. It's a pleasure. I think I will expand on a topic that also you've already touched upon, which is the DSL, and I will give more a broader overview on different DSLs and different modes that we have, and we have been adopting in different models within the ESiWACE project. So I'm representing a large team of people that you can see here. And I wanted to start first with the motivation of why we are developing DSLs. And if I'm allowed to give a graphical representation of what a weather and climate model is, I think I describe it as a multi-layer domain system. In a sense, it's multidisciplinary. First, we have the layer of the science. And again, here are different layers. First, we'd have the physical model. Then the scientists would come with a mathematical description of that model. And we have many of them actually within a model. And it goes all the way until what particular grid, what particular discretization or algorithms do we use now so that we can convert that into a program, into an implementation. Excuse me. Then the other layer is more the computational science side of it, because we need to map that into one of the supercomputers that we have available. And even though we know that the linear scaling, we are not anymore in the linear scaling regime, we keep getting more increasingly powerful machines. This is an example of the first exascale machine frontier. Every time we're getting more and more powerful machines, and they also come with a cost, which is the complexity. So we need to put our models into those machines. Really large scaling, we need to do our proper domain composition and communication efficiently to work on those machines. And this is done within the model. Then as we go inside each of those nodes that we have in this supercomputer, we are going to get a particular device that we need to program with a particular programming model. And we have many. We have a large diversity that we can choose. And once we go for a choice, this has to be adopted in the entire model code base. Finally, not least, even if, for example, OpenSCC would be supported by various GPUs, graphical processing units, there are always computer architecture specific optimizations, specific intrinsics or tunings that you have to do to really make it work efficiently. And all this layer goes inside the model the same as the science. This is otherwise put is what Eva already mentioned. For the example of the unified model, all of the optimizations, they are hard-coded within the model. And that makes it actually hard to make it portable or to adopt a different architecture. So the architectures and supercomputers are moving faster, I dare to say, than we are able to adopt our models. And it's also well known that adopting large models, simulations, to new devices is a multi-year, multi-people effort. So it's a really considerable effort. And that's one of the main motivations for developing DSLs. I can give also graphically a very simple example that illustrates what I'm saying. This is a computation of a gradient. It's very elegant, very simple in a mathematical form. But as we go into a particular implementation, we see kind of visually what is the ratio of code infrastructure that we need and optimizations. We need to deal with loops and data layouts. It was again mentioned by Eva that a DSL was abstracting data layouts and things like that. So it all goes in this direction, in the sense that the real information, it's here highlighted in bold, the real information, scientific information that you want to express in the scientific layer of your model. And that's the so-called separation of concerns. We like to separate this science from the optimization and architecture-specific implementation. Again, same graphical representation, and the idea of the DSL is that right in the middle, we are developing a language that allows to the user describe only the science and is abstracting everything else that you have to do. And the hope is that excuse me, the hope is that this is getting under control this friction that there is between large codes that contains a lot of complex science and the complexity that we need to adopt in order to be able to run on these large machines. So in ESiWACE, we are developing actually, or we are not developing DSLs. So our mission is to adopt and establish DSLs within real existing and operational models. The DSLs are also developed within other European efforts and other projects. And we are already targeting different DSLs or different modes, and I will try in the following to explain that. So one type of DSL is the one that brings us higher in abstraction. They give us a domain, they give us a language, and they allow us only to implement what is supported by that language, and all of the rest, it is eliminated from the language. So you don't need to implement for loops, you don't need to implement memory layouts. If I take again the same example as before of the gradient, I just reduce everything else, that it was infrastructure and optimizations, and this is the core of the information that I need. How do I map these now into a computer, into a programming language, into a programming model like OpenECC? That's not the role of the scientist. The language allows you just to describe this layer. The compiler will take care of the rest. Another approach is a lower abstraction, where the idea here is to leverage existing implementations that are there, but without really advanced optimization. So for example, say you have the implementation of a gradient in a simple triple nested loop written in Fortran. And the main idea of these type of DSLs is not to have to rewrite, because the previous approach, I forgot to mention, it implies a full rewrite. There is a new language we need to describe. We need to re-implement our model in that language. In contrast, in this approach, the strategy is to try to leverage existing codes that are already in production, but they follow very regular patterns in how it is implemented, and they don't incorporate these advanced optimizations or programming models for GPUs, for example. And the main approach is that the DSL here would parse this language. Since we adhere to really strict rules on how we are expressing our algorithms, we know that we are going to have triple nested loops, we are going to have arithmetic computations on arrays and so on. Then the DSL can parse these, bring this information inside the compiler, and then generate a completely different code at the backend side of it. So it's a completely different approach.
To wherever you want. Yeah. Yeah.
Sorry, anyone on the mic?
Yeah, that'd work. Small volumes probably.
All right. Yeah, I was saying it's a completely different approach, and there are advantages and disadvantages, or like different characteristics. And one of the clear advantages of this one is that this is more an evolution. We want to operate on existing codes without having to rewrite, which should be more the revolutionary mode of a DSL. So this is a picture of what exactly we are targeting in ESiWACE. On the high-level abstraction, we have a Python DSL with a new language, and we are porting the ICON dynamical core and other components of ICON into that language. And we also have the Fortran DSL that we just saw presented by Eva from Elfric. So that I won't go into those. I mean, I won't repeat, of course. I mean, it was already a great presentation. And the other one I will present also is the NEMO mode, which is also supported by Cyclone, and that's the lower abstraction where Cyclone is capable of actually taking operational code of NEMO, parsing it, and doing the compiler optimizations of the DSL without any other changes into NEMO. Okay, I will start with the high-level DSL for ICON. For those that follow a little bit the developments, we started with the first version of a high-level DSL in Python with a compiler called Dusk and Dawn, and then gradually we transitioned into a next version that is called GT4PIs, a newer version, and this is developed by Exclaim and by CSCS. So it's developing a different project, and ESiWACE, we are adapting it to ICON. That's the architecture of the compiler, nothing new. I mean, a typical compiler design for these high-level DSLs, we'd have a front end, in this particular case is in Python. The look and feel is very much like NumPy, as you will see. And then we have a compiler with intermediate representation, optimizers in between, several passes until you get to the final intermediate representation that goes to the code generation. Right now we have C++ and CUDA for NVIDIA GPUs. And the gray layers, they are not yet implemented. It's just to show that the architecture design allows to do these things. And following the previous question, for sure, at that level of the intermediate representation, one could also dump into days or any other backend generation or compiler. Okay, that's an example of the look and feel of the DSL for the front end. You will see at the right at the top, the fill operator. We express with the decorator in Python that this operator should be parsed by the DSL and should be processed by the DSL. And in this particular case, we're doing a neighbor reduction. We are computing, sorry, I should say we are in a triangular grid in this case, but that's not really matter because we don't express the topology. The topology of the mesh is abstracted, so we can operate internally with whatever topology. But we have vertices, we have cells, and we have edges. And in this particular case, we are computing at the vertex a variable that is a neighbor reduction of the neighboring cells. And in the case of a triangular grid or hexagonal, we'd have 6 neighbors. But it does not really matter, it's very flexible. The NumPy look and feel comes with this neighbor sum, and here on the right, you see the axis. I'm not sure if people can see the cursor actually, but I will just mention in the neighbor sum, we have this axis. This is similar to, you can? Okay, great, thank you. It's similar to NumPy, where in a dot operation, you specify which dimensions you are reducing. But what is specific to the DSL is the topology information that we can express, whether we go from vertex to cell, from vertex to edges. And this is really flexible. You can define those keys in your language. Then we have another decorator for composing a program, and the program can compose multiple operators all together until you build a full model, and then the compiler will have access to the entire information of your program for optimizations. This is a more elaborated example just to show that it's not only a simple vertex to cell, but you can do a cell to edge to cell to edge, and you can compose as much as you want. In this particular example, if you traverse, we start computing at the cell center and we fetch neighbor edges. From the neighbor edges, we go to neighbor cells again, and we are on the outer cell center of these triangles. And from this cell center, we go again back to the edges. And that will give us, this traverse will actually touch all the edges that you see in this diagram, and we are building larger stencils. That's a pattern that we encounter commonly in dynamical cores. And the language is very flexible, allows you to do all that. Again, on a Python NumPy kind of environment. So the status of it is we have an entire die core. It's around 100 stencils, and it's all already implemented and integrated in the model for operational configurations. This is the performance that we get on fine-grained, also on a first approach of porting stencil by stencil, so every kernel individually, and we did not yet do the effort of fusing or doing further optimizations. So already doing that, we are 10 to 20% faster, and overall 1.4 faster than OpenECC. And the remark here is that that's the operational OpenECC version, which is already quite well optimized, but more will come over time. More things that are coming are tracer advection. People are working on the tracer advection to have a full, not dry die core, but to have a full die core. And then Exclaim probably will work also on other physical parameterizations. Good. I should move now to the other mode, which is Cyclone. On the left, you see the revolution. That was a previous talk. On the right is the evolution. And that's the approach where I mentioned we take NEMO, existing code, and we parse it through the DSL, and we generate efficient code for GPUs also, and for CPUs for sure. That's the architecture of the compiler in this case, it is very similar in the end. They are all similar. So we have a front end, but of course the front end is different. It doesn't expose to you a language. It does the parsing of the existing NEMO code. But it will go into the PSI-IR, and there you have all the optimizers or transformations. And finally, you have different backends. The Fortran backend that allows to do also OpenMP and OpenSCC, we'll see, but there are also other backends like OpenCL or SIR backend that are being developed. I will show some lines on the SIR backend. This is what is great about this is that it already works for the entire model. So there is no porting exercise. It's already working. It was on May 2020 that they got full support for operational configurations, in this case, Orca-1 of NEMO. At the time, yeah, the performance of the GPU was at par with the Skylake. One might argue, of course, there's much more potential, but this is what this plot is showing, how over time, the great thing about this approach is that the model remains the same. You don't need to modify, you don't need to re-architecture, redesign, or re-engineer your model for a different architecture. And just over time, the compiler team is working on optimizations. And as of today, we are 3.6 speed up when we go to GPUs. That shows in general the approach or the benefits of the DSL. The model is already done, and then the team underlying can work on a particular architecture and all the optimizations, and speed up will just come. That's a similar picture for the scalability. So they went all the way to do an scalability exercise with until 150 GPUs, so quite substantial. Yeah, I'm not sure exactly at the highest point. That's not continuous scaling, but that could very well be due to the domain sizes that you get on some GPUs. But the main message here is the good numbers that you see, for example, in Jewel's booster with GPU Direct. There were some optimizations in the communication here performance. It really shows how you can massively go for an entire model into many GPUs. What about other architectures? Well, the Cyclone team is working on OpenMP, and now the idea is again the same. The model doesn't change, but we have another backend that is doing the OpenMP offload, and therefore it can target AMD GPUs, for example. That's an example. I should move a little window here. Yeah, that's an example of the different optimizations that we have seen on NEMO GPU. First, we start with the original code, and then we see the OpenSCC release. That was the first thing that happened. Then another boost in optimization came with OpenMP. That's not so much related to OpenSCC versus OpenMP, but to the fact that they implemented a little different strategy and optimizations for the release that came with OpenMP, just to clarify. And finally, the really large performance came with additional tweaks. Since Cyclone is generating Fortran code plus OpenSCC, it's actually giving you it allows the engineer, the HPC engineer, to go inside the code and then do further optimizations. And when they did that is when they achieved this 3.6 speed up, which shows the potential. And now the exercise is bringing all those manual tweaks inside the compiler, which is work in progress. Finally, I wanted to mention a word on interoperabilities, because an obvious question, since we have been showing like different modes and different DSL, an obvious question is, can the community aim at more standardized and uniform compilers, or we will always have to address one DSL per model? And that's an exercise, a task that we have in ESiWACE. And the idea here was to connect the two that I was presenting via intermediate representations, what we call this SIR. This particular case, we are taking benchmarks from NEMO. We are parsing that with Cyclone. Cyclone will produce the NEMO IR, and the NEMO IR now gets converted into SIR that we can pass to the other compiler. I think it's an important question. It goes in the lines of the question that Peter was asking before. Could we couple this to another compiler, to another backend? Could we couple this to DAIS? And I think this is actually showing that yes, it is important to talk about that so that we have similar concepts in our IRs, but it's certainly possible, feasible, and probably recommendable. And this, probably I'll have to skip the details of this graph, but it's to show that this exercise already shows interesting properties. Like, for example, in this case, we combine the two compilers and we see the blue is operating very well on the low domain size regime, and then it goes down a little bit, while the other compiler has actually different behavior. And when you saturate enough the GPU is when it gives you better performance. And this is just an interesting exchange for the DSL compilers. I think I should conclude. So the summary, the main take-home message is that the DSLs for weather and climate are actually maturing, and we are seeing that we are already working with operational code, not benchmarks or dwarfs anymore, but with real codes and operational configurations. And the main good message also that we have seen along these years is that the models now remain more stable as they are already implemented, or in NEMO, it was always from the beginning the case. And we have seen that over the time span of a couple of years, 3 years, then the compiler team just keep working on performance optimizations, and we have immediately seen that on the operational configurations. And I think with that, I can close. Thanks a lot.